body, 2 points on the body, A and B. And so now, as we have seen before, velocity vector of any point in rotation, let's say in pure rotation there is no translation in this case, will be perpendicular to the position vector, right? So velocity is omega cross p plus dp by dt. This component will be along the length of the vector. This component will be perpendicular to the vector. So in this case we have only pure rotation. So let me see if I can join these two. Okay. The velocity vector for velocity at point A will be perpendicular to OA, and at point B will be perpendicular to OB, like that. Okay, because the body is rotating in this direction. Okay. Now, velocity of A, velocity of B with respect to A is velocity of B minus velocity of A. Now, since the body is in pure rotation, you do not have this component. So, okay. So you have only omega cross position of P minus omega cross position of A. Omega cross position of B minus position of A. So position of B minus position of A is basically this vector. Yeah, this is your position of B minus position of A. Okay, let's draw it here. This is B and this is A. So let's say this is unit vector d cap. Okay, and the length of AB is LAB. Okay, so this is theta dot k cap cross LAB, which is length of AB d cap. So this is theta dot LAB k cross d, again cross product, k cross d is perpendicular to, so this is your t cap. So the relative velocity vector will be perpendicular to the line joining both the points. That's the whole point we're trying to make here. Relative velocity between 2 points in a body in pure rotation will be perpendicular to the line joining both the points. Okay. Now we have done the differentiation of a vector d by dt. So we'll define the operator is d by dt of any vector is rate of change of magnitude. We are putting that in parenthesis plus omega cross the vector. This is our operator. Okay. Velocity omega cross p plus you have dp by dt. Okay, so how many vectors we have? 1, 2 and 3. So when you do the differentiation operator, each vector will give you 2 components: rate of change of magnitude, rate of change of direction. So you have 3 to 6 components. So you have your acceleration is dv by dt, which is first vector omega. D omega by dt magnitude cross p plus omega cross p. Rate of change of magnitude, rate of change of direction. For the second one, omega cross dp by dt plus omega cross p. Okay. And the third one, plus omega cross dp by dt plus what did I do? Now first we're doing the magnitude and then the direction, right? So let us keep it in that same sequence. Avoid confusion. Okay. D square p by dt square plus omega cross dp by dt. Now this will go to 0, omega plus omega is 0, and then you have two of these terms, and so now you will have total 4 terms. Acceleration is equals to d square p by dt square plus 2 omega cross dp by dt plus you have d omega by dt is nothing but alpha cross p, and then you have finally omega cross p. Okay. Directions of each of these. Okay. You have the vector p. You are simply taking second derivative of the magnitude of p. So the direction of this is along, let us define the unit vectors, t cap, and let's say this is t cap. This component will be along t cap. Omega cross dp, even this is along d cap because it is only rate of change of magnitude, not direction. So this is also along d cap, but then you have omega cross dp. Omega is what is the direction of omega? Omega is k cap, right? Theta dot k cap. It is out of the plane of the paper. Direction of omega is out of the plane of the paper. So you have omega is theta dot k cap. Okay. So k cross d, this component will be along t cap. K cross d will be t cap. Okay. Alpha cross p. So this component will be along, alpha is also same, theta double dot k, so it k cap cross p. So this is also along t cap. Omega cross p. Omega cross p is along t cap. Again omega cross of that will be, if you do again omega cross of that, k cross t is minus t. So along minus t, radially inwards. Acceleration of point P is d square p by dt square plus 2 omega cross dp by dt plus omega cross p plus alpha cross, this is AP in parenthesis, This is we are calling Coriolis component. That is superscript Coriolis component. This is omega component, and this is alpha component. Okay. So what is magnitude of Coriolis component is simply 2 times omega cross dp by dt. So 2 omega, let me write this properly. Omega k cap cross dp by dt d cap, right? So this will be 2 omega p velocity, right? Omega component will turn out to be omega square p. So here your v is square root of dp by dt dpx by dt square dpy by dt square. Yeah, again p is the magnitude. Alpha will be alpha times p. Okay. Now finally, if you have an ordinary differential equation, let's say a dx by dt square plus b dx by dt plus cx plus d equal to 0. In order to solve this ordinary differential equation in MATLAB, you need to write this as, this is a second order ODE. You need to write this as 2 first order ODEs. So for that, you need to use the state space representation. We'll say y1 is x, we'll say y2 is dx by dt, then your y1 dot is y2 and y2 dot is dx by dt square, which can be written as minus b y2 plus c y1 plus d by a. So now you have written one second order ODE as 2 first order ordinary differential equations. So now the initial value problem can be solved in MATLAB using ODE 45, which uses RK45 method. And then here you need to give in MATLAB your ODE FUN, which is a function which takes initial values and of y1 and y2 and computes y1 dot and y2 dot. So ODE FUN takes inputs y1, y2 and time, and then initial values of y1, y2 and time, and outputs will give as y1 dot and y2 dot. Okay, and here you have to give your time span 0 to t, and then you have your y1 time t equals to 0, y2 at time t equals to 0. Once you give this, your ODE function in MATLAB will solve the ordinary differential equation and give you both the values of theta and theta dot, or sorry, y1 dot and y2 dot,